Assalamu alaikum dear students. Today we are going to start chapter number 11 from Advanced Engineering Mathematics by Krasik, edition 10. This chapter is about Fourier analysis and we'll be learning following topics from the chapter like Fourier series, Fourier integrals and Fourier transforms. So let's start with the introduction to Fourier analysis. This is a way to analyze complex waveforms and it was discovered by a French mathematician and physicist, Jean-Baptiste Joseph Fourier, who lived from 1786 to 1830. Fourier was studying the way heat was transmitted through solids, and in this process, he discovered a remarkable mathematical result. He discovered that any continuous repetitive wave shape could be built up out of harmonic sine waves. His discovery included a mathematical technique for determining how much of each harmonic was present in any given repetitive wave. This decomposition of an arbitrary repetitive wave shape into its component harmonics is known as Fourier analysis. So we can think of Fourier analysis effectively serving as a mathematical prism, because the way prism works to make rainbow colors from the white light, Fourier analysis transforms time signals to different frequencies. So Fourier theory basically consists of two major concepts like Fourier series and Fourier transforms. And in Fourier theory, our target is to represent a signal or function in terms of sine and cosine functions. So Fourier series, we can approximate any periodic function with the help of Fourier series, and we can find Fourier transform of any non-periodic function. And both the concepts are useful for both type of functions, that is continuous and discrete type of functions. So the starting point of Fourier analysis is Fourier series. They are infinite series designed to represent general periodic functions in terms of simple ones, namely sines and cosines. This trigonometric system is orthogonal, allowing the computation of coefficients of the Fourier series by use of the well-known Euler's formulas. Fourier series are very important to the engineers and physicists because they allow the solution of differential equation in connection with forced oscillations and the approximation of periodic functions. So the second expansion is applying Fourier series is to non-periodic phenomena and obtaining Fourier integrals and Fourier transforms. Both extensions have important application to solve differential equations. In digital age, the discrete Fourier transform plays an important role. Signals such as voice or music are sampled and analyzed for frequencies with the help of discrete Fourier transform. An important algorithm in this context is the fast Fourier transform. So let's define periodic functions. A function fx is called periodic function if fx is defined for all real x except possibly at some points, and if there is some positive number p called a period of fx such that fx plus p is equal to f of x. That is, function fx is said to be periodic with period p if f of x plus p is equal to f of x for all real x, wherever the function is defined. So f of x plus, we can say that, or we can conclude from this result that f of x plus np is equal to f of x. For instance, if we consider f of x plus 2p, then it can be written as f of x plus p plus p. And since function is periodic and its period is p, so we can write it as f of x plus p. And using this result, this is equal to f of x. So similarly, we can see that f of x plus 3 is also equal to f of x, and continuing this way, f of x plus np is equal to f of x. So the graph of a periodic function has the characteristic that it can be obtained by periodic repetition of its graph in any interval of length p. The smallest positive period is often called fundamental period. So there are few examples of periodic functions like cosine function, sine function, tangent function, cotangent function, and period of cosine and sine function is 2 pi. Similarly, period of tangent function is pi. And there are few examples of non-periodic functions like polynomial functions, exponential functions, and hyperbolic functions and logarithmic functions. There is an observation that fx is equal to tangent x is a periodic function that is not defined for all real x, but undefined for some points. That is for the points where x is the odd multiple of pi by 2. So we have already discussed it in previous slide that if fx has period p, then it has period 2p, 3p up till np. But the fundamental period is the least positive number for which f of x plus p is f of x. This is called the fundamental period of the function. So here are graphs of periodic functions sine and cos with different frequencies. Now the question arises, why do we need Fourier series and what is the use of Fourier series? What are the benefits of Fourier series? So let's have a look at a few of them. Many phenomena in nature repeat themselves. So Fourier series might make sense to approximate them by a periodic function. Secondly, Taylor series can give a good local approximation, but the Fourier series give good global approximation. Thirdly, Fourier series still works even if ft is not periodic. We can make it periodic to make it work for and represent in terms of Fourier series. Fourier series gives us a means to transform from the time domain to frequency domain and vice versa, which makes easier to see things in one domain as opposed to another. So in order to represent a function in terms of Fourier series, our problem will be the representation of various functions of period 2 pi. In this case, we are going to discuss the functions with period 2 pi in terms of simple functions sin x and cosine x. And this is called trigonometric system. So the series to be obtained will be trigonometric series, and we are going to assume that this is the series of this type. A0 plus A1 cos times cos x plus B1 times sin x plus A2 times cos 2x plus B2 times sin 2x and so on. Or it can be written in sigma notation as shown in 1. Where A0, A1, B1, A2, B2, that is all A's and B's are constants, and these are called coefficients of the series. And we can find the values of these series by Euler's formula. Hence, if the coefficients are such that the series converges, its sum will be function of period 2 pi. That is, this series will represent the function. So here we go. This is the Fourier series approximation for any periodic function with period 2 pi. Fx is equal to a0 plus sigma n varies from 1 to infinity. A sub n cos nx plus b sub n times sin nx, where a0 can be evaluated by this formula, and rest of an's and bn's can be evaluated using these formulas. That is, a0 is equal to 1 over 2 pi times integral from minus pi to pi of fx. Similarly, an is equal to 1 over pi times integral of minus infinity to minus pi to pi fx cos nx dx. Similarly, bn is defined by 1 over pi times integral of fx sin nx from minus pi to pi. So let's find out. There is an example and let's find out the Fourier series for the given function in this example. So function given here is fx is equal to minus k if x lies between minus pi and 0, and fx is equal to k if x lies between 0 and pi. And this function is periodic with period 2 pi, that is f of x plus 2 pi is equal to f of x. So we have to find the Fourier series, that is we have to find this series for this function. Fx here is this function. Now we know that the formulas for a naught, an and bn, so we are going to evaluate using those formulas. So first of all, a naught. We learned from previous slides that a naught is equal to 1 over 2 pi times minus pi to pi fx dx. So our function is piecewise defined. So in the interval minus pi 0, its value is minus k, and in the interval 0 pi, its value is k. So we are going to split this integral into two pieces. So 1 over 2 pi times minus pi to 0, and here fx is minus k, so we are going to plug in this value dx, and plus 0 to pi k dx. So after evaluating these integrals and adding them up, we have a naught is equal to 0. So this is just a matter of integration, very simple integration. So we can find out that value of a naught is equal to 0. So value of an is equal to 1 over pi times minus pi to pi fx cos nx dx. So again we are going to plug in the value of function which is defined piecewise. So we have to split this integral into two parts. So for minus pi to 0 interval, the value of the function is minus k. So this will become 1 over pi times integral from minus pi to 0 minus k cos nx plus 0 to pi k cos nx dx. Now let's evaluate these integrals, and we have this. So cos of integral of cos nx is sine nx divided by n. So minus k times sine divided by sine nx divided by n plus k times sine nx divided by n, and its limit of from minus pi to 0, and this part limits are from 0 to pi. So by applying the limits, again we have 0 because sine of 0 is 0, sine of pi minus pi x is also 0, sine pi x is 0, sine of 0 is also 0. So since all the terms are going to be 0 after applying limits, so an is also 0. Now bn. So we have formula for bn, which is equal to 1 over pi times minus pi to pi fx sine nx. And again, since function is defined piecewise, so we have to split this integral into two parts. So first part is for the limits minus pi to 0, and in this limit value of the function is minus k, so we plug in the value of the function here. And for the next part, next interval 0 to pi, value of the function is k, so after plugging in we have this integral. Now evaluate these. So 1 over pi times k cos nx, because k is constant, and this is not going to contribute in the integration part, so we can factor it out. So integral of sine nx is negative cos nx divided by n. So negative will make it positive, so we cannot see negative sign here. So in this case, minus k is the constant, and integral of sine x is minus cos nx over n, so we can see negative sign here. So after applying limits, we have these terms like cos of 0, because when we plug in the value of x equal to 0, so we have cos 0. We can factor the common terms out, like k over n, so k over n pi is factored out, and inside we have cos 0. And when we plug in this limit, we have minus cos of minus n pi, again negative sign with this term, and upper limit gives us this term, and lower limit gives us this term. So we know that cos 0 is 1. So cos 0 is 1, cos 0 is 1. So we have 2 here, minus cos n pi, the cos of minus theta is equal to cos of theta. So this is also equal to cos of n pi. So when we add both to negative 2 times cos of n pi, so we have two common factor, and inside we have 1 minus cos of n pi. And cos of n pi is minus 1 to the power n. So that is cos of n pi is minus 1 when n is odd, and cos of n pi is 1 when n is even. So when cos of n pi is 1, the value of bn becomes 0, whereas when cos of n pi is minus 1, the value of bn becomes 4k over n pi. So here we have, so after plugging in the values of n, we have different values of b's. That is, for n is equal to 1, b1 is equal to 4k over pi, because when n is equal to 1, we have cos of pi. Cos of pi is minus 1, so negative will make it positive. We have 2 here, so 2 times 2 is 4, 4k over n is 1 pi. So b2 is 0. Because n is even, this is the value of cos of n pi is 1. b3 is 4k over 3 pi, because n here is 3. Similarly, b4 is 0, b5 is 4k over 5 pi. So ultimately, after applying the limits, we have after plugging in the values, we have a naught is 0, we have a n 0 for all n. So a naught 0, that is, this term will become 0, a n 0, these cos terms will become 0. So b's are 0 when n is even. So the only values which contribute in the series are the values of n when n is odd for this term. So for b is equal to 1, we have b1 sine x. So you can see that 4k over pi sine x. When n is 2, this is 0. When n is 3, we have b3 sine 3x. So b3 is 4k over 3 pi. So 4k over 3 pi sine 3x. b4 again is 0. So this term will become 0. For n is equal to 5, we have b5 sine 5x. So we have 4k over 5 pi sine 5x, and so on. So this is the required Fourier series. So if we approximate this function for finite number of terms in the series, then these approximations are called partial sums. Like if we have n is equal to 1, that is, if we consider only first term, then this is called S1. This is called partial sum of including one term only. If we consider two terms to approximate the function, then this is called partial sum including two terms, that is, this is called S2. And if we include three terms to approximate the function, then this is called S3. So these are the partial sums. So let's see how does it work. So this is the original function. If we take the if we approximate the function with first term only, so we can see this type of wave, because this is 4k over pi times sine x. So this is the wave for S1, and you can see that it does not approximate the function well. Now if we have if we consider two terms, first two terms, then that is, if we approximate the function with S2, then this is the terms including in the approximation 4k over pi sine x plus 1 over 3 sine 3x, and this is the graph of the right side of this equation. That is, this is the graph of S2. This is the graph of S1. We have already seen. This is the graph of S2. Now, if we consider these three terms, you can plot these graphs with the help of any software and verify it. So if we consider these three terms, you can see that this graph becomes like this. They are repetition of the wave in this portion, and they are, you can see, repeated wave in this portion, and rest is almost the same like in S1, S2. So continuing this way, here we go. If n is 1, that is the graph of S1. If n is 3, that is graph of S3. We have already seen in previous slide. If n is 5, that is graph of S5. And if n is 101, that is graph of 101, the S101. So you can see that it approximately the same function which we intended to approximate through Fourier series. So here you can see again, for different values of n, you can see the graph of Fourier series. And you can see error becomes smaller and smaller as number of terms increases. So error decreases as number of term decreases. So again, you can see the Fourier series for different values of n. So as it approaches to infinity, or as n becomes larger, the graph of Fourier series actually becomes graph of the original function. So here are a few questions from the exercise 11.1. Question number 6 to 10. Graph of 2 pi periodic functions. We have different functions, so let's try to graph these functions. F of x is equal to x, and this is very well known function, and you know how to graph it. So this is the graph of f of x. F of x is equal to sine x. Absolute value of sine x means that this is going to be positive for all values of x. So no point of the graph lies below x-axis. So all the points, as we know that the graph of sine x looks like this, right? Now, since this is the absolute value of sine x, this wave will also shift here, right? So you can see this is the graph of sine x magnitude. That is sine x absolute value. F of x is equal to e to the power negative x mod or e to the power minus x mod. Both have same graphs, and the graphs look like this. Similarly, we have function in question number 9. Fx is equal to x when x lies between minus pi to 0. So, and x is equal to minus. So, minus pi to 0, it has this graph, and from 0 to pi it has this line, which is pi minus x, and this is x. So find the Fourier series of given function which is assumed to have period 2 pi. So in this section we are going to approximate the functions with period 2 pi with the help of Fourier series. So in question 13, fx is given by the function in problem 9, that is fx is equal to x when x lies between minus pi and 0, and pi minus x when x lies between 0 to pi. So let me write the function here. Fx is equal to x and pi minus x. X when x lies between minus pi and 0, pi minus x when x lies between 0 and pi. So we have to find the Fourier series, that is we have to find all the coefficients a naught, a n, a bn, and plug in the values of the series. So first of all, let's find out the value of a naught. A naught is equal to 1 over 2 pi times minus pi to pi fx dx, and again this function is defined piecewise, so we have to split this integral into two pieces. So 1 over 2 pi times minus pi to 0, we have different definition, 0 to pi we have different definition. So minus pi to 0 integral of x dx and then integral from 0 to pi of minus pi x dx. Now let's evaluate these integrals. So this is very simple evaluation, a simple integration. Integral of x is x square over 2 minus pi to 0 is the limit, and pi minus x, integral of pi minus x is pi x minus x square over pi, and 0 to pi is the limit, and after plugging in we have a naught is equal to 0. Now let's find out the value of an. So value of an is equal to 1 over pi times minus pi to pi fx cos nx. So again, function is defined piecewise. So this is the interval minus pi 0, and this is the interval 0 pi. So from minus pi 0 x times cos nx, and similarly from 0 to pi integral of pi minus x cos nx. Now this integration is a little bit tricky. So we'll integrate both the integrals one by one, and then after that we will substitute these values back to this equation, and we'll find out the value of an. So let's evaluate integrals first. So first integral, x times cos of nx, we have to integrate with the help of by parts integration, and we'll have this result. In couple of steps we'll have this result, and after applying the limits we have this result. Now when we plug in the limits, the sine 0 becomes 0, and x is also 0, so this term becomes 0, and cos of n x is cos of 0, so 1 over n square is here. When we apply the lower limit, then we have sine of pi x, sine of minus pi x, which is again 0, and we are left with negative of 1 over n square times cos of n pi, because cos of minus n pi is equal to cos of n pi. So let's keep it safe and evaluate this integral now, this one. So integral from 0 to pi, pi minus x. So we have two integrals. We can write it as sum of two integrals. So this is the value of cos nx dx, integral of cos nx dx. That is the first integral, which is equal to 0. And the second integral is x cos nx dx, and we have already discussed that. After applying by parts integration, we have this value, and after applying limits, we have this integral is equal to 1 over n square cos n pi minus 1 over n square. Now we have value of both the integrals, then an becomes this. So 1 over pi times integral value of this integral, which is equal to this 1 over n square minus 1 over n square cos n pi, plus pi times integral of value of this integral is 0, so pi times 0, minus integral of this this integral value of this integral is 1 over n square cos n pi minus 1 over n square. So after simplification we have this, and ultimately we have this value, because 1 over n square minus 1 over n square is 0, so we are left with 1 over n 1 over n square plus 1 over n square is becomes 2 over n square, negative 1 over n square cos n pi becomes minus 2 over n square cos n pi. So let's factor 2 out. We have 2 over and factor 1 over n square out, so we have 2 over pi n square times 1 minus cos of n pi, and cos of n pi is minus 1, as we have already discussed. Cos of n pi is equal to minus 1 when n is odd, and equal to 1 when n is even. So we can see that value of a1, since n is odd, its value cos of n pi is equal to minus 1, and 1 minus cos of n pi becomes 2. So a1 is equal to 4 over pi because n is 1 here. A2 is 0 because for all the even values of n, cos of n pi is 1, 1 minus 1 is 0. So 1 minus cos n pi becomes 0 whenever n is even. So all the values of a when n is even are 0. So similarly, A3 is 4 over 9 pi. That is 4 over, that is all the values of an when n is odd are 4 over n square pi, right? So since for A3, n is 3, so 4 over 9 pi. Similarly, A4, because n is even, value of an is odd, an is 0. And when n is 5, that is n is odd, then 4 over n square pi, that is 4 over 25 pi. Now we have to find the values of Bn. So formula for Bn is 1 over pi integral from minus pi to pi fx sin x. And again, function is defined piecewise. So we have to split this integral into two parts. And we'll be calculating one by one both the integrals. So first integral is minus x sine of nx. Again, with the help of by parts integration, we have this result, and after applying the limits, we have this result. Now consider the second part of the integration, that is pi minus x sine of nx, which is equal to pi times, again we can write as it as sum of two integrals. So pi times 0 to pi sine nx, negative of 0 to pi integral of x sine nx. So evaluating these two integrals one by one. So first integral, that is integral from 0 to pi sine nx, is equal to this, and the second integral x times sine nx from 0 to pi is equal to this, and this is again calculated with the help of by parts integration. So by adding these two results, this and this, we have the value of this integral, right? Pi minus x sine x, which is equal to n over pi. So Bn, so now we have to plug in this value into this equation in order to find the value of Bn. So Bn is equal to sum 1 over pi times sum of these two integrals. Now the value of first integral is this. So let's substitute the values. So we have 1 over pi times minus pi cos of pi n, and plus the sum of these two, the value of this integral is the sum of these two integrals, which is equal to pi over n. And so the value of Bn is equal to 1 over pi times minus pi over n cos n pi plus pi over n. Again, cos of n pi depends upon the value of n, and when n is odd, cos of n pi is minus 1. When n is even, cos of n pi is plus 1. So by factoring pi out, we can cancel pi by with pi, this pi. So we are left with minus 1 over n times cos of n pi plus 1 over n. So for different values of n, we have values of b. So whenever n is even, you can see that value of Bn is 0, and whenever n is odd, so we have values of Bn which is not equal to 0. So we can figure out what is the value of Bn when n is even. So when n is odd, this value of cos of n pi is minus 1. So we have 2 over n when n is odd. Bn is equal to 2n when n is odd, is equal to 0 when n is even. So next step is to find the series after substituting all the values. So we also have a naught is equal to 0, and there are the values of b's and a's written here. So let's find out the series. So this series can be written as this, and let's substitute all the values. So this is the required series, or we can write it as 4 over pi times cos x plus 1 over 9 cos 3x plus 1 over 25 cos 5x, so on, plus 2 times sin x plus 1 over 3 times sin 3x, so on. So this is the required series. Similarly, we have question number 14. We have to find the Fourier series for this function, which is fx is equal to x square, and it is defined in the interval minus pi to pi, and it has period 2 pi. That is, it repeats itself after the interval of 2 pi, that is f of x plus 2 pi is equal to f of x. So again we have to so let's first of all see the graph of the function. This is the graph of the function, and if we see the periodic function in different intervals, we can see it repeating itself after every interval of length 2 pi. So here is the value of a naught. I am not going to get into all the details. This is just a matter of integration. You can solve it yourself. All the solution is shown here. So you just need to put the values in the formula and integrate this x square, and after integration we have the value of a naught, which is equal to 2 pi square divided by 2 into 3, that is, which is equal to 2, cancel out, just cancel this out. So we are left with, let me write, pi square over 3. So this is the value of a naught, and value of an, again use this formula to find the value of an. 1 over pi times minus pi to pi fx cos nx. This is the basic formula for an, and substitute the value of fx, which is x square. Again we need to use integration by parts, and in this evaluation we have to use by parts integration a couple of times in order to get the results, and you can see the calculations written here. So which is equal to minus 2 pi over x. So again integrating by parts, we have this. So an is equal to this. So for different values of n, we can find out the values of a. So as we have already discussed, that cos of n pi is equal to minus 1 to the power n. That is, this is equal to minus 1 when n is odd and 1 when n is even. So we have this value of an, that is, after simplification we have this, and for n even, since minus 1 to the power some even integer is equal to 1, so we have by 4 over n square, and when n is odd, this is negative of 4 over n square. And bn is equal to 0. You can calculate it yourself, so do it yourself. Bn is equal to 0. So ultimately we have this series. A naught is equal to pi by 3, as we have already calculated in previous slides. A1 is equal to 4. So what is the series? So let me write the series first, and then you can an cos of nx plus bn sin of nx. So Bn is equal to 0 for all n. So that is why you cannot see any sign term in this series. And a naught is pi square over 3. So this is the value of a naught. And a1. So let me write few values for a's. A1 is equal to 4. A2 is equal to, a1 is equal to minus 4. A2 is equal to, when n is even, 4 over 4. So A3 is equal to, when n is odd, minus 4 over 3 square. Similarly, A4, when n is even, 4 over 4 square. So you can see that. So negative 4 is factored out, and inside we have cos x. When n is 1, this becomes cos x. When n is 2, this becomes cos 2x. When n is 3, this becomes cos 3x, and so on. So this is the required series for the function fx is equal to x square, which is defined in the interval minus pi to pi, and it has period 2 pi. So now we have question number 16, and the function given is shown in the figure. So first of all, we have to extract the function from this figure. So this function, you can see that is defined from minus pi to pi, and this line shows that in this interval value of the function is 0. Similarly, in this interval value of the function is 0. So let's write the function fx is equal to 0 when x is between minus pi and minus pi by 2. And from this, the value of the function is, you can see that this point is half of pi, half of pi. So this is the graph of y is equal to fx. So this, it means fx is equal to x when x lies between minus pi by 2 and pi by 2. Again, after pi by 2, that is between half of pi and pi, again value of the function is 0. So this is 0 when x lies between pi by 2 and pi. So this is the function, and you can evaluate all the coefficients, that is a0, a1, an and bn, in order to find the Fourier series. So you can use this function to evaluate all the values. I'm not going to solve in detail, so again do it yourself. And so here is another function which is given in terms of figure. So again we have to find out the function or extract the function from this figure. So you can see from the figure that this function is also defined in the interval minus pi to pi, and it has period 2 pi. That is f of x is plus 2 pi is equal to f of x. So let's find out the value of fx from this figure. So in the interval minus pi to 0, this is represented by this line, and from 0 to pi, this is represented by this line. So we have to find the equations of these two lines. So if we have if we consider this line, so there are 2 points given on the line. This point is minus pi 0, and this point is 0 minus pi, right? So we can use 2 point formula in order to find the equation of line, that is y minus 0. Let me consider the point here. So slope is y2 minus y1, that is minus pi divided by x2 minus x1, that is pi, so times x plus pi. Okay. So it means y is equal to minus x minus pi. So this is the equation of this line. That is, so if we have to write value of the function, so fx is equal to minus x minus pi for x lies between 0 and minus pi. And for this interval, this line passes through 0 pi and pi 0. So these are the points on this line. So let's find out the equation. Y minus 0 is equal to, so slope is again minus pi over pi times x minus pi. So this is minus 1, so minus x plus pi. So this is minus x plus pi when x lies between pi and 0. So this is the value of fx, and again you can find the coefficients a0, a and bn with the help of this definition of function, and you can also find the series. So we have to use this function. So again, do it yourself. So that is all for today. Next time we'll be learning the Fourier series for the functions with the period not equal to 2 pi. That is any the functions with any arbitrary periodic functions with any arbitrary periods. So till then, take care. Bye bye.